There you go.
Thanks, Claire. Yes, I'm going to be talking about the successor to the currently under development at the UK Met Office, LFRic, which some of you may or may not be aware of. So nothing to do with current generation access, unfortunately. So a little bit out of the scope of most of the talks we've heard today and yesterday. So what is LFRic? So yes, it's the next generation non-hydrostatic atmospheric model that's currently being developed at the Met Office. There's a scheduled deployment date of 2026 for LFRic to go operational, and the Bureau's stated goal is to be operational within 6 months of the Met Office, so by implication 2026 or 2027 here as well for NWP. It's a bit of a confusing name if you're not familiar with the folklore. So it's named for Lewis Fry Richardson, who is the first person to attempt to undertake a numerical weather prediction computation, which he did 100 years ago using what he called computers, but what we would call people. And someone took the trouble to make these really, really beautiful pictures 100 years ago of how this could be done. So he had this whole conceptualization that there'd be all these computers, there'd be domain decomposition between the different computers, they'd pass messages to each other in order to solve the equations. I think he didn't use the QG equations or anything. I think he actually used the Boussinesq equations or something. So it was comparatively pretty ambitious. Unfortunately, there was a computational mode in his calculation, so it went unstable, and he didn't know anything about that at the time. So that was unfortunate, but nevertheless, it was a very heroic attempt. So 100 years later, he gets a model named after him, which is very nice. So I guess the first question is, why do we need a new atmospheric model? Why can't we just use the forever? And probably the most immediate answer to that is the so-called pole problem. So if we decompose our domain into, a whole bunch of local regions, then you can kind of imagine that at the pole, there are all these different sort of domains that are all going to be interacting with each other. So there's going to be a lot of message passing between a lot of different processes at both the North and the South Pole. And so as you scale up to sort of order sort of hundreds of thousands of processes, that amount of message passing is going to sort of saturate the amount of time that the model takes to execute, and it's going to lead to big scalability problems. So that's the sort of the most immediate and pressing reason to get away from the sort of latitude longitude grid that is so intuitive to all of us and so nice to work with. Another compelling reason is that finite difference methods, they have a stencil, and that information from that stencil has to be passed as messages between neighboring processes. If you move to a finite element method, the stencil is basically just the interface along the elements. So it's much less data that needs to be communicated between elements. So the size of the messages are smaller. So that helps with scalability as well. So getting away from the latitude longitude grid does present some problems, however. And the main one is that on a latitude longitude grid, everything is natively orthogonal. So horizontal wind, zonal and meridional winds are orthogonal to one another. There's no projection between the two, basically, apart from maybe some machine precision noise. And also normal and tangent vectors between cells are the same either side of the cell. So that's very, very nice. When you move to a non-orthogonal grid, like a cubed sphere, which is generated by some sort of gnomic projection or some other method, you no longer have orthogonality between the edges. And so you need to be very careful about how you represent fluxes and tangent vectors and things like that between the elements in order to ensure that they are uniquely defined along those interfaces. So mixed finite elements specifically can help us with that, because there are different metric transformations for different finite element spaces that can guarantee the continuity of vector fields and tangents between edges, which is really, really nice. So also, we can, the other big motivator is improved representation of dynamical processes. So what this specifically means is conservation, so conservation of mass and vorticity in particular, but also balance relations, so geostrophic balance and hydrostatic balance as well. And so getting these things right on an unstructured grid really pushed LFRic towards a mixed finite element formulation. Also, it's worth noting that I believe the first cube sphere model was actually the CCAM model out of CSIRO about 30 years ago now. So CSIRO have done some major innovations in this space in the past as well, which is great. So in terms of the dynamics, as I said, they're using a mixed finite element formulation. So what that means is we have these family of different sort of finite element spaces, and here's a kind of cartoon of what they look like here. So we've got different polynomials which are orthogonal with respect to the vertices of the element, the edges of the element, the faces of the element, and the volume of the element. And these things have different amounts of continuity. So polynomials which are orthogonal at the vertices have derivatives defined in all 3 dimensions, so you can apply a gradient to these things. Polynomials on the edges only have their derivatives defined in tangent directions, so you can apply a curl to these. Polynomials which are defined on the faces only have a derivative defined in a normal direction, so you can apply a div to these. And polynomials defined within the volume are discontinuous everywhere, so they're not differentiable. And one of the nice properties of this sequence of finite element bases is that the grad, the curl, and the div actually map you from one basis to the next. And so once you've got this property, you can then go and prove that you've got things like the divergence theorem and the circulation theorem, and that's what buys you the conservation laws that I talked about on the last slide. So yes, they have that the curl annihilates the grad and the div annihilates the curl, and they've got the divergence and circulations theorems baked into them, which is very, very nice. In terms of the time discretization, so the spatial discretization, both as a cube sphere and as a finite element method, is a big leap from the The time discretization, they're actually quite similar. So they're still using a semi-implicit model so that it can target both global and regional NWP type applications for a compressible system. So there's an outer solve, which basically solves for the full coupled system of the velocity, the pressure, the density, and the temperature. Then there's an inner solve, which is a Helmholtz problem for the pressure. And then that solve is preconditioned using a multi-grid method for scalability across very large process accounts. So there's a future plan to move to what's called a hybridized preconditioner, which means introducing constraints along the interfaces of the elements that enforce the continuity of the winds across element interfaces, and then to solve for those constraints. That's not part of the trunk of ALFRic yet, but that's kind of one of the strategies moving forward in order to increase performance. So one of the challenges with ALFRic is that the horizontal grid is unstructured, as opposed to the which is just a latitude, longitude grid. So it's got a very nice logical structure. And what this means is that when you extract entries of an array, you've got to use indirect addressing. So you can't just, you have to use some sort of indirect addressing map to actually get entries out of an array. So this leads to a degradation of performance. So there are several different things that have been put in place to negate this issue and improve the performance. One is mixed precision. So some parts of ALFRic use 64-bit real, some parts use 30-bit, 32-bit. Some parts of the code also use I-first indexing. So typically, K, we use K, the index that goes up the column, as the first index, because, most of the physics and things happen in the column. But there are some aspects of ALFRic that actually loop in the horizontal first in order to ameliorate this problem of the indirect addressing. And then there's the hybridized preconditioner that I just mentioned previously. Okay, so what are we doing with the with ALFRic at the Bureau, and where are we going? So the physics for ALFRic was forked from the a couple of months ago now, so it's now an entirely separate development. And so we've got a global GAL7 configuration working at NCI with a lot of help from Paul and Martin and other people who contributed to this. We've also got an idealized RAL2 configuration. So the RAL2 configuration currently in ALFRic only really works over the ocean. So it's just idealized at the moment. There are plans for a coupled GC5 configuration to be released in October this year, I believe. There'll be a GC6 version developed after that, but that'll really only be developed for developmental purposes. It won't be publicly released. I believe it's just going to be used as a baseline for the GC7 development, and then GC7 will be released. I believe that's the plan, but I don't know the precise timeline on that. There's also an RAL3 project that's starting up, I believe, this September, and I think there should be a first release of that about September next year, I think is the aspirational date at the moment, and that's a 2-year project. So I think they're hoping for a final release of that in September 2024. So yes, as I say, we've got these running on, we've got the GAL7 and the idealized regional configurations running on NCI at the moment via the on-demand service that NCI put together as a successor to ACCESS-Dev. And we've also got regridding tools running there, so we can take a start dump and regrid it onto the cube sphere and use it as an LFRic start dump to run from as well. So as well as LFRic, there's a whole forest of other NGMS tools that are coming online over the next couple of years, most of which I know basically nothing about, so I can't speak to them in any detail. There's a bunch of different visualization tools. So LFRic uses NetCDF as its output file format, and it's on an unstructured grid, so visualization needs to be handled differently from the So Wolfgang Hayek at NIWA has implemented a LFRic reader for Power View, which is very, very nice. There's also a couple of Python-based visualization tools that have been developed at the Met Office. One is enhanced support for LFRic files in Iris, and another is a tool called GeoVista, which I don't know very much about. I believe it might be using Xarray, but I might be getting it confused with something else there. There's also these regridding tools, which we have implemented at NCI as well. So verification, so Ver has been replaced with Met Plus, which I believe is from NCAR. Someone can correct me if I'm wrong about that. Nemo, which you can debate whether that's a next generation model or not, but that's where the Bureau is going for its ocean model component. And then data assimilation. So Chun Su spoke a lot yesterday about JEDI, so I won't speak too much more about that, but JEDI will be replacing the various data assimilation tools in use at the Bureau as well. Okay, so what are we doing at the Bureau around LFRic, our current and future plans? So right now we're implementing a whole lot of automated testing. And the reason we're doing this alludes back to some of the comments that were made yesterday about the difficulty in working with the Met Office and getting changes propagated back up into the code base. So our aspiration is to be able to run the trunk of LFRic nightly, pick up any bugs basically when that happens, and have pretty good confidence that we can always build and run the latest version of LFRic. And then if we want to get our changes back into LFRic, we want to do that at the latest release as quickly as possible. We're trying to increase our upstream collaboration with the Met Office for this purpose as well. So we want to really have very tight relationships with the LFRic developers at the which we think will also help us to get our changes in. A couple of examples of that are the work that Jörg Heinrichs is doing on the Cyclone library. So Cyclone is a domain-specific language, as Paul talked about yesterday. So what it does is it takes code from LFRic and it auto-generates more optimized code for a particular target architecture, so that the developer themselves doesn't have to worry too much about optimization. That can be done by the automated code generation. We also want to collaborate with the Met Office on some enhanced numerics features, which we're sort of talking to them about. Also training. So we've started putting together some training materials on LFRic, and that's been delivered in a first round at the Bureau, and we'll enhance those materials as more LFRic functionality becomes available and roll that out more widely as well beyond the Bureau. And that's a partnership with another next generation project at the Met Office called Next Generation User Experience. So we're feeding our training materials back into that as well. So that's another way that we're trying to partner more tightly with the Met Office. And also we're very keen to work with the ACCESS-NRI, you know, if and when LFRic comes on your radar in the future. So thank you very much.